Hello friends, I am Snehal and today we are going to talk about the centripetal force in circular motion, motion of a vehicle along a curved road and banking of roads. So let's begin. So we studied about the centripetal acceleration in previous lectures. Let's recall it. So suppose this is an object performing circular motion in anticlockwise sense. So we know that the velocity of an object performing circular motion is always directed tangential to its path. So for this object, the velocity at this point will be directed like this. When it reaches at this point, the velocity will be directed like this in this direction. When it reaches at this point, the velocity will be directed like this vertically downwards, and at this position the velocity will be directed in this direction. So we see that there is always change in direction of velocity, and that's why we say that there is some acceleration acting on an object performing circular motion. So the acceleration is called as centripetal acceleration because it is directed along the radius of circle and toward the center. So centripetal means along the radius and toward the center. So it's the centripetal acceleration acting on this object which is changing the direction of its velocity at each and every point. So we know the magnitude of centripetal acceleration from previous lectures is v squared over r, where v is speed of the particle and r is radius of the circle. So now, according to the Newton's second law, there must be some force acting on this particle or an object performing circular motion which causes this acceleration called centripetal acceleration, and that force we call it as the centripetal force. Okay. So the centripetal force acting on this object, let's suppose it is F suffix Cp. Fcp is m times, that is mass of the object times the acceleration using Newton's second law. So it is m times a suffix c, which is equal to m times v squared over r. So this is magnitude of the centripetal force. Now we can represent the centripetal force in vector form too. So for that we need a unit vector directed along the centripetal force. So the centripetal force is directed along the radius and toward the center of the circle. Now recall the radius vector r bar is directed towards the position of particle starting from the center of circle. So we want a vector just opposite to that. So if we take minus of r bar, we get a vector which is directed along the radius but towards the center. So using this I can represent the centripetal force in vector form. So in vector form I can write this as Fcp bar equals to this magnitude mv squared over r multiplied by unit vector in its direction, which would be minus of r cap. Okay, so minus of r cap. So this is the formula for the centripetal force in vector form. Now let's consider some examples of centripetal force to get some idea about it. So let's suppose that this object in this example is the stone tied with a string. So in case of stone tied with a string, the centripetal force is provided by tension in the string. Okay, it's the tension in the string which keeps on pulling the stone towards the center, and due to which the stone keeps on moving in a circle. Then we can take several examples of centripetal force. So for an example, motion of an electron in an atom. So we know from the classical theory of an atom that electrons revolve in circular orbits around the nucleus. So let's suppose this is an electron which revolves in circular orbit around this nucleus. So electrons are negatively charged, nuclei are positively charged. So here the centripetal force required for motion of an electron is provided by the electrostatic force of attraction between negatively charged electrons and positively charged nucleus. So the centripetal force FCP is equal to the electrostatic force, and using the Coulomb's law of electrostatics we can write down its magnitude. So it is some constant multiplied by charge on nucleus multiplied by charge on electron divided by r squared. So this is the centripetal force acting on an electron performing circular motion around the nucleus. Let's take next example. Planet revolving around sun. So we know that the planets revolve around the sun in elliptical orbit, actually not exactly circular one, but for any curvilinear motion, closed curvilinear motion, some centripetal force will be required. So for a planet which revolves around the sun in elliptical orbit, the centripetal force is provided by obviously the gravitational force of attraction between the planet and the sun. So FCP is equal to the gravitational force, and we can write down the magnitude of gravitational force using the Newton's law of gravity, and it is the gravitational force is universal gravitational constant g multiplied by mass of the sun multiplied by mass of planet divided by r squared. So gravitational force between two bodies is equal to universal gravitational constant g multiplied by mass of first body multiplied by mass of second body divided by r squared. So this is the centripetal force acting on a planet revolving around the sun. The gravitational force provides the centripetal force. Now let's talk about motion of the vehicles along the curved roads. So let's suppose that this is a car and it is taking turn on this road. Now we can think of this road as a part of a big circular road whose center lies somewhere here. So in that sense, when this car takes a turn on this road, it is performing circular motion, and we just saw that some centripetal force is required for an object to perform circular motion. So the question is, where does that force comes from? So to think about the answer, let's suppose that you are sitting in a car and that car is taking turn like this towards left. So you might have observed that you get an outward jerk towards right. So you feel that there is some outward force acting on you, but in reality there is no such force. So what happens is, you are moving in a straight line and due to your inertia you try to continue your straight line motion, and it's the car which is taking turn like this. Okay, so every part of the car, the windows, the roof, everything is moving towards left. So in reference with the car, you feel that you are moving towards right. Okay, so in reality there is no such force. So due to this your straight line motion and motion of a car, curvilinear motion of car, you tend to slide on the seat of the car. Now think which is that force which keeps you from the sliding. So answer is simple, it's the frictional force. So it's the frictional force which keeps you firm on the seat of car and which completes your circular motion along with the car. Okay. So which would be the force which provides the centripetal force for this car? It would be the frictional force. So it's the static frictional force which avoids the slipping of the car on road surface and provides necessary centripetal force for the circular motion of the car. Now let's try to find out the maximum speed with which this car can take a safe turn. So for that, let's draw all the forces acting on the car. So what I am drawing now is the back view of the car. So let's suppose car looks like this when viewed from back side. This is road surface. Now what are all the forces acting on the car? So one is force due to gravity acting downwards. The other one is force due to the road surface acting upwards, the normal reaction. N, and third force is the static frictional force which provides the required centripetal force. Okay. Now the car is not flying away in this vertical plane, so we can say that for vertical equilibrium, normal reaction must balance the gravitational force. So I can write that for equilibrium in vertical plane, normal reaction balances the gravitational force, so N equals to mg. Okay, and static friction provides centripetal force so I can say that F suffix s is equal to mv squared over r. Okay. Now for the maximum speed, let's say Vmax, the static frictional force will attain its maximum value. So I can say when V equals to Vmax, Fs becomes Fs max, and if speed is increased beyond this limit, then friction won't be sufficient to provide the required centripetal force. Okay, and the car will slip away. So I can say that when V is equal to Vmax, Fs becomes Fs max, and we know from previous lectures that Fs max, the maximum value of static frictional force, is mu s times the normal reaction. So substituting these two, I get, or Fs max is equal to m times Vmax square over r. M times Vmax squared over r is equal to mu times mu s times the normal reaction, and we saw that normal reaction is equal to mg. So which is equal to mu s times m into g. It is m times Vmax squared over r. Now we can cancel out m and take this r on the other side. So we get Vmax square equals to mu s into r into g, and then taking square root on both sides, we get the maximum safety speed limit on a curved road equals to square root of mu s into r into g. Now we have seen that the safety speed limit for a horizontal curved road Vmax is equal to square root of mu s into rg, where g is acceleration due to gravity, which is a constant, r is radius of curvature, and for a given turn we can say that it's a constant. The only thing which can change here is mu s, which is coefficient of static friction. So for a given turn, that is for a fixed radius of curvature, Vmax entirely depends upon the coefficient of static friction, and we know that friction is not reliable. For an example, let's suppose that there is some oil spread on the road surface, or in rainy season the road surface is wet, then the coefficient of static friction in those cases will be very less compared to the normal coefficient of static friction, and therefore the static friction will not be sufficient to provide the necessary centripetal force for the turn, and therefore there are more chances of skidding of the vehicles. So what we do to avoid this is that we use a trick, and the trick is called as banking of roads. So let's see it. So what is banking of roads? So in banking of roads, the outer side of the road surface is raised with respect to the inner side with some angle called as angle of banking, and we will see that this method provides necessary centripetal force even in the absence of static friction. So let's see how. So this is a vehicle moving along this curved banked road, and this is back view of the same vehicle. Now let's draw all the forces acting on this vehicle. So obvious forces are the gravitational force acting vertically downwards, mg, and the force due to this road surface which acts perpendicular to the road surface, the normal reaction. So in this case it will act in this direction like this. Now question is, in what direction the static friction will act? So to find out an answer, let's go to this diagram. So let's consider motion of this vehicle. So we know vehicles which are moving along the curved roads have tendency to skid away from the center. So here this vehicle will have tendency to skid in this direction. That means the static frictional force which avoids the skidding, it will act opposite to that, so it will act in this direction. Okay, so in this diagram the static frictional force acts in this direction along the road surface. So this is normal reaction, this is static frictional force. Now we need to resolve all these forces in two perpendicular directions. So question is, in what two perpendicular directions should we resolve them? So answer is simple. The center of the curved road will be somewhere in the horizontal plane. So the centripetal force acting should act in the horizontal plane. That means in this direction. So one direction is fixed, that's why we need to resolve forces in this direction, the horizontal direction, and perpendicular to that. Okay, so let's resolve the forces. Now this angle is theta, and this line is horizontal, this line is also horizontal, so those are two parallel lines, and this is like an intercept. So I can say that this angle is also theta. So we can resolve Fs in two components. So component in horizontal direction will be Fs cosine theta, and component in this perpendicular direction, let me use some different color for it. So this is component of static friction in vertical direction, so it is Fs sine theta. Okay, then similarly this angle is theta, this total angle is 90 degree, so this angle is 90 minus theta, and again this angle is 90 degrees, so this angle should be theta. All right, so now we can resolve the normal reaction also. Let's resolve normal reaction. So the component in this direction will be n cosine theta, and the component in horizontal direction will be n sine theta. Okay, now for the equilibrium of this vehicle in vertical direction, the forces in vertical plane should be balanced. So let's write down equations for the equilibrium. So for equilibrium in vertical plane, we can write the total upward force, which is n cos theta, is equal to total downward force. So n cosine theta equals to Fs into sine theta plus mg. Okay, then I can substitute the value of Fs, the static friction. So Fs is mu s multiplied by n. I will substitute that here, and I will take the terms containing n on left hand side. So this becomes n cosine theta minus Fs sine theta, and Fs is mu s times n. So mu s times n into sine theta equals to mg, and we can take n common from this. So n times cos theta minus mu s into sine theta is equal to mg. So I can call this equation number 1. The second equation we will get from the forces in horizontal direction. So in horizontal direction, Fs cos theta plus n sin theta combined, they provide the necessary centripetal force for turning. Okay, so centripetal force is provided by forces or net force in horizontal plane and we want to find out the optimal speed, the maximum speed. That's why I can say that total force, which is, let's check once again, it is Fs cos theta plus n sin theta. So Fs cos theta plus n sin theta is equal to, I will say, mv squared over r, but v will be v max. okay, because we want to find out the maximum safety speed. Then similar to this first case, I can substitute in place of Fs mu s multiplied by n. So this is mu s times n into cosine theta plus n sine theta, and that is equal to mv squared mv max squared over r. Again, I can take n common from this equation also. So taking n common, I get mu s cos theta plus sine theta equals to m v max squared over r, and this is my equation number 2. Now what I will do is I will divide this second equation by the first equation. So doing that, what I get is dividing equation 2 by 1. So n and n in these two equations will get cancelled on left hand side. So what we are left with on left hand side is mu s times cosine theta plus sine theta divided by cosine theta minus mu s into sine theta. So divided by cosine theta minus mu s into sine theta is equal to m times v max squared over r. This was from equation 2, okay, and in equation 1 we have mg on the right hand side. So dividing by that, m and m gets cancelled, then r and g we can take them on the other side to get the maximum safety speed, okay. So I will take rg on this side. So rg multiplied by these terms in the bracket. So I will write this as sine theta plus mu s into cosine theta divided by cosine theta minus mu s into sine theta is equal to v max squared, okay. And if we take square root on both sides, then what we get is v max is equal to square root of this term. So this is the maximum safety speed limit for a curved banked road. So this is the exact formula. Now as I told, even if we neglect friction, so even if I make this coefficient of static friction equal to 0, still we are left with some speed limit, okay. So that means banking of road provides some necessary centripetal force even in the absence of friction. So let's find out that limit. So let's make mu s equals to 0. So in an ideal case of absence of friction, that is mu s equals to 0. Let's substitute that. So we'll get rid of this term as well as this term. Then we are left with sine theta over cos theta, which is tan theta. So I can write that speed limit V max becomes square root of Rg into tan of theta, okay. So theta is our angle of banking. So we can see that even if the friction is 0, for non-zero angle of banking there will be some safety speed limit.